Yeah, good morning. Can you hear me now?
Yes, sir.
Okay. So I'm using mic. I cannot hear your voice now. So if you have anything to say, please text me on chat box. Thank you. So did I complete polarization or did I start polarization? Did I start polarization or not? Please text me on chat box. Did I start polarization? This is section A, I think. Yeah. Yes. Text me on chat box. Did I start polarization? No. Okay. So just wait a minute. Right. So this. Yeah. Did I discuss the slide? E of this representing this P as PA roof plus PB roof e power minus JK dot R. Did I cover this slide about polarization? This one or this one? No? This one? Did I talk about this? Anything you have, please text me on chat box. I cannot hear you now. Okay, then fine. So I think I'm done. So we are done with section C. Okay. So I will discuss polarization. So it is orientation of electric field, or I can go for magnetic field. So orientation of electric field on the transverse plane when wave is propagating transverse to the transverse plane, on which of course you have the trace of electric field, and that is what this polarization. So you know all those things already. So we know that generally this E is perpendicular to K. Okay. Now, what I can say, so the polarization vector, when I take polarization vector, we take it as P. And this P must fall within the plane perpendicular to K. So this P must fall within the plane perpendicular to wave vector K. So I know this already. So for example, we have a transverse plane, all right? And say some wave is piercing through. Say a wave is piercing through, say it is along G axis and propagation is along Z. So therefore I can take wave vector along Z. So now you have, this is my transverse plane. So this XY plane is your transverse plane. All right. So now we have transverse components. If wave is propagating along g-axis, Ex, Hy, Ey, Hx are transverse components. So they are transverse components and are transverse to one another. So now, for example, I can trace a circle now, you see. Let me trace a circle. Say that EM wave in its course of travel is tracing a circle on this transverse plane. Okay. Now to support this argument, let's take a vector. Say this is a vector P. See this vector P, this is what my polarization vector. This vector P is rotating along this circle or on this transverse plane. And now we take some two directions. So this is say, let me take two directions. I take this color. So this is a direction A roof, and I take one more along this. Okay, this is a direction B roof. And from this figure, it is evident that A is perpendicular to B and this is perpendicular to K. So now what we do, we will decompose. So decompose the polarization into two orthogonal directions. So polarization into two orthogonal directions, A and B. Okay. So what are we going to present is this. So my polarization vector P, so I can decompose into two orthogonal stuff, PA roof plus PB, say B roof. Yeah. So these two are directions. I have direction A and direction B. Otherwise, I have orthogonal directions A and B. So my P is equal to PA PB. Having said, I don't save it. Not a problem. So we know our EM wave, our electromagnetic wave, or our E wave. Readily, what we have, E of R. E of R is P e power minus jk dot R. All right. And also we have backward traveling wave. This is forward traveling wave with polarization vector. And also I have backward traveling wave. And for the time being, we are neglecting this backward traveling wave. Let's consider only this forward stuff, P e power minus jk dot R. Now we resolve this P into orthogonal stuff. So therefore we will plug in that. So now E of R is PA roof plus PB B roof and e power minus jk dot R. Okay. Now, this is important. Normally, this PA and PB, so these two components, so they are complex by nature. Yeah. So they are generally complex numbers, we can say, are complex by nature. So therefore, what do I do now? I can take down PA as, say, let me associate EA. So EA, and I'll take something like e power j phi a. Okay. Anytime, whenever you have these things, you can assume them as complex quantities. So PA, PB, for example, you see you have an equation like this. We derived an equation for electric field is polarized along x-axis, spatially varying along z, and also time varying t. So what we have is, we just took like this, right? Ex naught cos omega t minus we have wave number k naught z plus some phi1, some initial phase, and also you have some backward traveling wave. By convention, what we have is this particular stuff. By general, this particular stuff is complex. Okay, that means I can, this is complex amplitude. That means I can show in polar form both in magnitude as well as phase. I can show that. And I can contribute this phi1 as this initial phase for this. Similarly, whenever you see this kind of components, you can treat them as complex numbers. So PA is just a minute. So PA is this, and then PB is also complex. So I take EB, e power j5b. See, the motivation behind considering EA and EB in PA and PB, it's because of one reason. We are just considering orientation of electric field for polarization, okay? So therefore, we included EA and EB respectively in this PA and PB. So once we have this, now just if you plug in this PA and PB in this equation, then you must have E of R is equal to EA e power j51, or it is j5a we took. So A roof plus EB e power j5b, and this is the direction B roof or B. So now this is e power negative jk dot r. All right. So this is a different stuff. So we plugged in this stuff here, and we observed this now. So e power negative jk dot r. Now from this, what we do, we will try to take this common. Okay. So therefore, ER is EA along direction A. So I have EB, and you have now e power j 5b minus 5a, and this is B roof. All right. Okay. So this is B roof, and now I took this already. So now it is e power j 5a and e power negative jk dot r. You must understand this e power negative jk dot r, this is oscillation component. Okay, wave is traveling, say, along this direction. This is k dot r, it's traveling along the direction. So it is oscillating along that direction. So we will associate other components to it. Okay. So now what I'll do is we will cut this first. Oh. Okay. This is decent. So we will cut this. Okay. Now we are going to interpret this as follows. Okay, so this component, this is like phase difference between. So this is phase difference between two complex quantities. Say you have PA and PB. All right, and you're seeing this over here, and this e power j phi a. So this is anyone. So this must be common phase difference, or this is, we could say, common phase otherwise. This is common phase, or this is common to both PA and PB. Okay. So now we will designate this. So this common phase, whatever. So this point we will take it as theta is equal to phi a. So we will designate like this, theta equal to phi a. And I have this phase difference between PA and PB, and that we will take it down like this. So the phase difference between PA and PB is delta is equal to phi b minus phi a. That's it. So we have a couple of quantities, theta equal to this common phase and phase difference between those two components. All right. Now we will use them. So let's use them here, and then we will. So you have E of R. So E of R is EA, A roof, plus EB. And now this is E power J. This is what? phase difference between PA and PB. We just plugged in over here. So and then you have this EB is along B roof, or it is in the direction of B. So that means EA is polarized along A, and EB is polarized along B, and there is a phase difference between EA and EB, that is delta. Okay. Now, so having said this, now what we take is e power j theta. Okay. So we consider theta equal to phi a for simplicity. So now you have, let's take one more color. You have e power negative j k dot r. Okay, this is the final form. So from this final form, what can we conclude? One second. So yes, so can we take e power j pi p as common and say, of course you can take, happily you can take. There is no way of saying that you have to take only e power j phi a as common, and the delta must be phi b minus phi a. There is no predominant rule like that. You can take anything. You can take j. So I just want to show, means we just want to show here that there is a common phase between EA and EB, and also there is a phase difference between this, I mean PA and PB. That could be phi a minus phi b or phi b minus phi a. Doesn't matter, anything you can take. That's a good question. Thank you. So this is what the final expression. So yeah, you have this as your final expression. Okay. So if you want to know this, EA is amplitude along direction A. Similarly, EB is amplitude along direction B. Okay, and you have theta as common phase and delta as phase difference. So you know all that. So now you can identify all these things like this. I can take a table describing this polarization. So I'll take it here. I don't have space. Let's quickly impress this in the form of tabular form and its mathematical definition. Okay. So yeah. And the very first one you have, that is linear polarization. Okay, linear polarization, we call it as ALP. Now, when there is no phase difference between these two components, say EA and EB or PA and PB, whatever, PA or PB, then when there is no phase difference, delta equal to 0. Okay. You just tell me, see, there is a common phase theta between EA and EB. That indicates that, that indicates that first of all, there is no phase difference. So this delta is only phase difference between EA and EB. So if that is 0, then otherwise we could say there is no phase difference between these two components, and this particular stuff is said to be linear polarized stuff. So this is linear polarization. And I'll go for one more, that is circular polarization. Okay, so circular polarization CP, this is straightforward. When there is a phase difference of 90 degrees between what EA and EB. Now, when I say 90 degree, whether EA leads EB or AB leads EA, so therefore we have a plus or minus 90 degrees. So in this case, and this must be, so if these two amplitudes remain same along A and B, so then, and if there exists this phase difference between EA and EB, Now, the traversing wave should undergo circular polarization. And we can trace this on the transverse plane. And this transverse plane is transverse to direction of propagation again. So, and again, you have two special cases under this. So that is right hand circular polarization, you say, or you say RHCP. And again, you have left hand circular polarization, LHCP. Okay. Now this one, if delta is equal to positive 90 degrees, okay, and provided for this to exhibit circular polarization, not only we require this, also we require the amplitudes must go equal. And for left hand circular polarization, this delta must be minus 90 degrees, okay. And again, EA is equal to EB. The most, the general case, what you have is elliptical polarization. So circular polarization and linear polarization, those two forms are special cases of elliptical polarization. He is Guru, okay, he is Guru, and these two concepts derived from this Guru elliptical polarization. So like circular polarization, you have RHCP, LHCP. Like this also you have right hand elliptical polarization and left hand elliptical polarization. Okay, so you have this. So what about this delta? Delta must be same, plus or minus 90 degrees. But in this case, for this to exhibit elliptical polarization, yeah, yeah, very good. Thank you. So for this to EA should not be equal to EB. Yeah. But coming to this guy, this linear polarization guy, what about the amplitude constraint? Yeah. Do you want to circumscribe anything? I mean, circumscribe means are you restricting anything in terms of amplitude for linear polarization? No. EA could be equal to EB or EA not equal to EB. Doesn't matter for this. For linear polarization, there is no dependence on the amplitudes, whether or not they are equal. We don't really bother that, okay, whether this is equal to this or not. But the only thing is that there must be no phase difference between two orthogonal components. I mean, you have along A roof and B roof, you have E and EB. So there must be no phase difference between these two. If we satisfy that, that must really satisfy linear polarization. Okay. And now, so let me show this. Which one? Yeah. Now this figure is from, this figure is derived from Dr. Raymond. So you see, here I have two waves. Let me open this with paint. Okay, here I have say two waves, and Mr. Uh, this is blue. I take blue. Okay, so this guy is along. This guy is along direction. This is my direction A, and this is red. So I take this, and this is along B. So we have two directions, A and B, and these two are orthogonal with respect to each other. All right. Now you tell me, see, I have EA oscillations. So my EA is oscillating up and down along this. This is my EA oscillations up and down. And therefore, along G axis, along this G, of course, I have K also along this G. This K indicates what? Propagation is along this G. So this is what your wave vector. So now you see your wave is oscillating along here, and it is spatially varying along Z. All right. So this is linearly polarized one, first of all. And also, if you observe carefully, you see along this B magnetic field. I mean, sorry, in this case there is no magnetic field. We have only two components, EA and EB. So EA is oscillating along A, EB is oscillating along B. Okay, so EB is oscillating along B. So therefore, you see, you have this is what your EB wave, right? So I have both EA and EB. Now just confirm this. This EA, this is my EA wave. Okay. Now you focus here, which color I can take. All colors are dominating. Let me take this black again. See, at this point, EA is equal to 0. EB is also 0 because both are starting say at this point. Okay. And now by the time you reached here, at this particular Z, at this particular Z, I can say what? So EA is maximum. At this particular G, Z means, Z. At this particular Z or G, EB is also maximum. And again, you come here. At this point, EA is coming to 0. Sorry, this black one, say this EA is coming to 0. EB is also say minimum, so 0 in this case. And again, at this point of Z, what happens is that EB is maximum, EA is also maximum. So therefore, there is no phase difference between EA and EB. And when you try adding these two components, EA, so this guy is Mr. EA, this guy is EA, and this red guy is EB. All right. So when you try to add these two, now what are we going to get? So we are going to get this green wave. Okay. Now you obtain this green wave like this. All right. Now there is a slant oscillations, but whatever, whether it is slant oscillations or vertical oscillations or horizontal oscillations, doesn't matter. It is simply linearly polarized. Yeah. So we are just showing here wave oscillation. A wave is varying spatially in one dimension, that's along Z. Okay, and that's the idea. So this is linearly polarized wave. And now we'll go for next one. You see, a circularly polarized wave is the sum of two orthogonal linearly polarized waves that are 90 degrees out of phase. You try to understand this. It is no big deal. For example, you see, let me take black. Now see this point, at this point, say this is my EA component, and this red one you're seeing over here, this is my EB component. Okay, so now you see this EA is the minimum here, this is 0. Now what about EB? At this juncture, EB is what maximum? You would see this. Are seeing this? EB is maximum here. Okay. Now coming to this all the way here. Now your wave is say propagating along Z-axis. So along this Z, as wave is propagating along Z, it is customary to take wave vector K also along Z. That means wave is propagating along Z. So now at this point of Z, EA is maximum. You see, EA is maximum. And what about this EB, the red one? The red one, this EB is minimum here. Okay. And again, at this point of Z, EA is minimum, but what about EB? So now this EB is maximum, right? So exact maximum and minimum happens at one point. So therefore, we could say there is a phase difference of 90 degrees. See, from here to here, I can account like this. From here to say here. Okay. So this must be a phase difference of 90 degrees. Because max and min will happen at this particular phase, so 90 degrees. So therefore, this is the case, you know what happens. And if you take, this is your transverse plane. Your transverse plane is this. On this, see, you're tracing a circle like this. Now it's propagating along Z. So wave vector K is along Z. Now see the polarization, the trace of the electric field, the combined, if you're going to add these two A and EB, the combined effect, the green one you see, the green vector is tracing a circle on this transverse plane. And therefore you could say you have circular polarization. Okay. Now again, you have two standards, IEEE standards and physicists. So based on physical means based on this physics. So this community and this community, so they just gave two different perspectives on whether it is RHCP or LHCP. If you want to know that, let me go with this. Where is that? I want that. Where did I put that? Let me check it out. Okay, I don't find it here. I have one figure for that. This is not. This is not. I don't have it here. Okay, anyways, I'll just show it later. So you have a figure because IEEE says, for example, you see, okay, I can draw it for you now. See, for example, you have a transverse plane, something like this. Okay, and say a wave is propagating, say, wave is propagating something like this. Yeah, so this is my transverse plane. So I have two components. What do I say now? X cross Y. So this, you just take right hand rule, say X cross Y is G. Okay, so G is this. Now, for example, if a wave is, this is my electric field vector, say it's tracing a circle like this. In its course of travel, say it's tracing a circle, it's moving all the way like this electric field vector, right? So you're just moving this way. If you're just moving this way, just take your thumb like this, okay? Right. You put your right hand thumb like this. So now this is along Z. This is along Z. I mean, your wave vector K is along Z now. Now, this is what you're, so this is nothing but right hand circular polarization. Just take your right hand, you curl your fingers on say XY plane, and this G is transverse to the XY plane, or this G is perpendicular to XY plane, and along G you have propagation, so that you can see you have right hand circular polarization. But physicists, I mean, according to physics community, they say this is left hand circular polarization. That means if I see from this view, if I see from this view, I have one perspective, and if I see from this view, I have another perspective. All right. So according to physics community, this is left-hand circular polarization, but according to IEEE community, it is right-hand circular polarization. Okay. So anyways, we will solve with an example. You'll understand what polarization we have and what is the 90-degree phase difference between EA and EB components now. So I don't save it. So orientation of electric field on transverse plane is what your say polarization. That's what you understood. Okay, let me take one simple example. Say I have my electric field and I have two components, say Ex cos omega t minus beta z. Okay, and say I have one more component, Ey cos omega t minus beta z c plus phi. So let's take two components like this. Okay, did I miss anything here? Shall we need to add anything here? Because on the left hand side you have vector definition, on the right hand side you are not showing anything. So you have to take here, say this is, why did I take this cap here? Just a minute. This is not required. So this is my, okay, so I just take, okay, so Ex is polarized along x-axis and Ey is say polarized along y-axis. Okay, in this case the wave is anyways traveling along positive z-axis. So you have two components. Say you have like this. I have xy plane. I have my xy plane now. So my Ex is oscillating along x-axis. So this is my Ex oscillations, okay, along x, and my Ey is oscillating along y. So this guy is Mr. Ey and this guy is Mr. Ex. So now we take transverse reduction. Okay, now this Ex oscillations, spatially it is varying along z. Okay, yeah, if I take phi equal to 0, in this case, phi equal to 0, then I can take like this, right? So if I add these two, waves, we will get a wave like this, slanted wave. It will oscillate like this now. So therefore, you would see a wave is going slanted along g-axis. So we'll see first of all whether you have linear polarization or circular polarization or whatever, or elliptical, whatever with this. Now we will freeze. We will freeze this propagation at z equal to 0. We'll observe what's going to happen at z equal to 0. So that z equal to 0 means what? I'm taking here beta z equal to 0. Okay. Now also you can freeze at t equal to 0. At t equal to 0 means in this case omega t equal to 0. And now we will have some cases for phi. So we will take first of all phi is equal to positive 90 degrees. And you will take phi is equal to negative 90 degrees. And also we will take phi 0 degrees. So 90-degree phase between Ex and Ey, 0-degree phase. Okay. Anyways, so we'll have now. All right. So say you have your Ex component. This is my x-axis, say, and this is my y-axis. Okay. Now, first one, what do? I take omega t is equal to 0 radians because I know omega is radian per second and this t is second. So you have units in radians. So just take phase in radians now. So whatever this entire argument is phase. So this is what radian per second multiplied by second radian, and beta is radian per meter multiplied by z in meters. So again, it is in radians. So otherwise, I can take beta as my wave is propagating along, say, that axis, say it is in free space. I can take beta is equal to a wave number k naught. So in lossless medium, if you have TEM propagation, I can take a wave number as phase constant. There is no big deal in that. So both have units radian per meter. Okay. And what this k naught talks about, this k naught says that how quickly the electromagnetic wave is varying in space is what this k naught. Okay, and this omega is talking about this, how quickly the electromagnetic wave is varying in time. Okay, so how quickly it is varying in time, so therefore you're multiplying by time. And how quickly your electromagnetic wave is varying in space, so therefore you're multiplying by space quantity z. In this case, we just took one-dimensional wave. Okay, So now what we do? So omega t is equal to the case one, we will take omega t is equal to 0 radians. Now what we get? So anyways, we made that equal to 0, omega t equal to 0. If omega t equal to 0, this is of course 0. So omega t equal to 0, z equal to 0. Omega t equal to 0 we took, and also we took, say, phi is equal to positive 90 degrees. Okay, and you plug in this phi is equal to cos 90, then what do you get? Anyone? What do you get now? What do you get now? You can speak out. I just unplugged my mic. You can speak out.
Sir, AY equal to, that is
EY
AY
will
equal
lag,
to
sir.
0, sir.
EY goes to 0, and what about EX? I mean, what about EX now? Will EX
Sir,
survive?
totally bar becomes EX, AX
Very
bar,
good.
sir.
Fine. So now, as you said, E is equal to EX like this. So I can take like this. Okay. And this particular stuff I can show like this. EX, AX proof. Right? Now, second chance, what do I do? Case if omega t is equal to 90. I mean, omega t I will take in radians. Omega t is equal to pi by 2 radians. If again I'm using mic, I cannot hear you. If you have anything, you can text me on chat box. If I take this is case 2, omega t is equal to pi by 2, and of course fix your phi is equal to positive 90 degrees. So omega t is equal to pi by 2 radians. Okay, so I put here pi by 2. So already z equal to 0. This is cos pi by 2 gone. So x is gone. I have omega t equal to pi by 2 here, z equal to 0, phi equal to 90. Okay. So anyways, this is now cos 180. So cos 180 is negative 1. So therefore you have minus ey ay. So now you have like this. If it is positive y, this is positive x, this must be negative y. Okay. So how did you come now? You just came all the way like this. From here, you came this way. Okay. Now you're going to tell me, yeah, according to IEEE standards, which one we're going to take. So again, we'll go for case 3. Okay. So omega t is equal to, I take phi. Otherwise, it is 100 degrees. Okay. 100 degrees. And again, phi is equal to same 90 degrees we take. So what we get, we took here omega t is equal to phi. Of course, z equal to 0. And now omega t equal to Mr. Pi, z equal to 0, phi 90. So what are we going to get now? So cos pi minus 0, it is cos 180. Cos 180 is negative 1. So you get negative EX. Okay. Now this is what here? 180. This pi means 100 degrees. So 180 plus 90 is 270. Cos 270 goes to 0. So there is no EY component in this case. We have only X component. And EX cos pi is negative EX AX roof. So therefore, I must go like this. All right. So on. You can just continue this process. I can take omega t is equal to pi plus pi by 2, 3 pi by 2. You can take for omega t is equal to 3 pi by 2 plus pi by 2, that is 2 pi. You take for same phi, phi is equal to plus 90, phi is equal to plus 90. Now slowly, if I take omega t is equal to 3 pi by 2, this is 3 pi by 2 means cos 270 is 0. This is 3 pi by 2, 270 plus 90. This is 360. Cos 360 is what here? Cos 360 is what? It is 1. So therefore, I'll get, okay, it's 1. So therefore, I get positive EY AY roof. So I just go this. Okay. So we traversed all the way and we're coming this way now. Now in this, if we restrict like this, if Ex magnitude is equal to EY magnitude. That means this length and this length in terms of magnitude they're same, then it will trace a circle on the transverse plane, and outside the board you have propagation. Okay, now you take your left hand, you just take your left hand. See, this is just moving clockwise. Okay, it's just going clockwise like this. Otherwise, take your left hand, you curl your fingers. You just curl your left hand fingers in clockwise direction. The thumb will point towards your eyes, towards your nose, or towards you, whatever. So along thumb, you have propagation, and along this curl is say on the transverse plane, you have left hand circular polarization. That's it. So IEEE community says you have left hand CP, but physics community says it is right hand CP because they see from the other perspective and they can think of it is right hand CP. But we strictly follow IEEE community standards. So therefore it is left hand circular polarization. All right. This is very simple. If this is unequal, if EX is not equal to EY, then you must have left hand elliptical polarization. So there is no big deal in this. Okay. Similarly, you repeat the same process. You repeat same process, but just different. Okay. So I remove this now. Oh. So okay. So I remove this. Okay. All right. I take this color. Now this time what you do, this phi, whatever phi you're seeing here, this phi is equal to, you take minus 90. Phi equal to minus 90. That's it. Just go ahead with this. And of course you have case one. Case one is what? Omega t is equal to 0 radians. You convert radians to degrees because you have mixed nomenclature. You have here radians and you have in degrees. So that you can convert, say you can convert radians to degrees. What is said in that? You convert this radians to degrees, it becomes 90, 180, so on. Just add with this degree and go ahead. This also phi equal to minus 90. So you have 1 through 5, you have 5 cases. You just go through all those things. Now in this case, what happens? If we maintain this equality, Ex equal to Ey in magnitude, and if you exercise for phi equal to negative 90 degrees all the way, then you would see right hand circular polarization. This time you would see anti-clockwise movement. Okay, direction is like this, anti-clockwise. All right, now you must take your right hand. This is what right hand circular polarization. So for phi is equal to negative 90 degrees, you get right hand circular polarization. For phi equal to positive 90 degrees, you get left hand circular polarization. Okay, so that is pretty straightforward. If for instance, if I remove this phi completely, or if you maintain phi equal to 0, now what's going to happen if I take phi equal to 0? So if I take phi equal to 0, you must get linearly polarized wave. That's it. So we will take 5 minutes break. We will take 5 minutes break just post 5 minutes from now. We will discuss for 5 more minutes from now, and then we'll take break. So yeah, I will remove everything now. Let me remove everything. Let's revisit our equation again. So you have equation for electric field is equal to, you have Ex cos omega t minus, I can take beta z or k naught z. So beta z. So this is polarized along, see, this indicates that this E wave is polarized along x-axis, but propagating along positive z-axis. Okay, I have minus of positive, say beta z. Okay, and again I will take Ey component. I have cos omega t minus beta z, and now I take phi, okay, and this is ay. Now ex could be equal or unequal, doesn't matter whether ex is equal to or unequal to whatever, doesn't matter. So if I maintain phi equal to 0, okay. Now again you have cases 1 through 5 all the way through 5. So case 1 is omega t equal to 0, so on omega t equal to 2 pi. Okay, you go in the interval pi by 2, pi, 3 pi by 2 for omega t, and phi is equal to 0. Maintain this. Now, anyone, what's going to happen now? You can draw it. Okay, so this is my say y-axis, and this is my x-axis. Now I take omega t equal to 0, phi equal to 0. Same condition again. If I freeze my stuff at z equal to 0, at t equal to 0, I'm seeing only vector. See, at z equal to t 0 and t equal to 0. Say at z equal to 0 means I'm on transverse plane now. Okay, I'm on the transverse plane at t equal to 0. So when I satisfy these two, what I can see on transverse plane, I can see only vector oscillations like up and down, okay, or like this. I can see only these oscillations vectorially if I satisfy these two stuff, conditions, z equal to 0, t equal to 0. So omega t equal to 0, z equal to 0, this is 0, this is 0. So cosine 0 is 1. So no second thought, I have a vector like this now. Ex. So this is my ax group. Okay. Now again, this is 0, this is 0, this is 0. Okay. So cosine 0, this argument is 0. So cosine 0 is 1. So it is ay, ay. This is positive y, this is positive x. So now you have a vector along y. All right. Say, okay, for simplicity, you can take ex equal to ey, or you can also go for ex not equal to ey, it doesn't matter. Now, you know what happens? Now, again, you take omega t is equal to 90. If I take omega t equal to 90, and of course, z equal to 0, so cos 90 is 0. So this is 90, this is 0. So this is again cos 90 is 0. So both are 0. Say you're here. You came all the way, you're coming to 0 again. Now I take omega t is equal to pi. If you take omega t equal to pi, this is cos 180. So cos 180 is -1. So you have like this. Let me take this color now. Okay, so this is negative ex. Say negative ax. Or ex multiplied by negative ax root. Okay, and this is cos 90 gone. Okay, so we took pi right, but pi cos 180 minus 1. This is also pi. What are you seeing now? Again, 0. There is no pi, 0. So here also you get negative ey. So therefore you have this. Okay, you can think of like this. And again, you can take 3 pi by 2. 3 pi by 2 means 0. It also 0. 2 pi, it's positive 1. It's positive 1 again. So what's happening now? So it's happening like this. You're oscillating up and down, okay, along y, and you're oscillating horizontally. Let me take another color. You're oscillating horizontally along x-axis. Okay, oscillating like this, vertically along y, horizontal along the x. So now what's going to happen if I add these two? Now anyone, what's going to happen? The resultant oscillations you will see like this. So let me take this way. Let me take this is your transverse plane. The resultant vector is something like this. Yeah, that's it. Yeah, along 45 degrees to xy. See, from y-axis or x-axis, it is just taking 45 degrees. So therefore, you will have to Yeah, that's it. Otherwise, I can show like this. Okay, I can show this way. It's oscillating now. So therefore, towards you, a wave will come like this towards you. This is also again a linearly polarized wave. So there is no right hand or left handed linearly polarized wave. So right hand, left hand will get associated with elliptical and circular polarizations, not with linear polarization. So you will understand these things when you study antenna course because of course uh, the polarization will become prominent when you deal with devices which are orders of wavelength. Okay, maybe this sounds not that pragmatic at this point of time, but in the latter stage, things will become much clearer. Okay, I have an antenna, for example, some antenna like this. Now I say that this antenna is vertically polarized. Okay, I have something like this. So now the radiation in one dimension I can see like this. So the electric field is oscillating just perpendicular to ground. This is your ground. So perpendicular to this, you have, I mean, a vertical polarization. If I tilt my antenna like this, let me tilt my antenna horizontal to ground like this. Now, you know what happens? This antenna will radiate in one dimensional technically, say horizontal polarization. Now, which is said to have a big losses, in this case, ground is what here? Ground is infinite sink or infinite source of charge. Any charge can go to ground or any charge you can take from ground. Okay. So now you know what happens, which is, so you can assume this ground is like a conductor, say. Now, who is tend to have more losses? Vertical polarization and horizontal polarization. You know, this guy will tend to have more losses. You know why? Because, for example, this guy, say, is, okay, let me take it this way. This is very important to understand again. So everything is important. Okay, there is, uh, let me take my surface. Let me take my earth surface. Say, I'm just taking something like this, earth surface. And say, let me take my horizontal polarization like this. Say, the wave is say, resting, say, on my earth surface. Now, in this case, what happens, the electric field will spend time with this. So for most of the time, electric fields are running parallel to this Earth surface. So therefore, Earth could capture energy from this. Yeah, Earth could capture or Earth could eat or consume energy from the waves. It will just go into the Earth now. All right. So if it is vertical polarization, now what happens is that electric field will interact with this earth for less time. Okay, just tip of the vectors is interacting with this earth surface. So from this, earth could capture less energy. All right, so therefore you will understand these things of course in antennas. So you have vertical and horizontal polarizations. For most of the applications, we choose vertical polarization so that energy, Earth can consume less energy from this vertically polarized wave. Of course, antenna will never radiate a one-dimensional wave. Okay, antenna will always radiate a three-dimensional wave, but we are considering its one-dimensional variation. So no antenna will radiate only a sine wave like this. Yeah, never. This is only a modeling, a one-dimensional modeling. And this sign assumption we considered because of time harmonics. We included this guy in our analysis, time harmonic nature. Whenever I say I have time harmonic nature, under steady state conditions, you could say that you have all sign variations because you're saying that your electric field and magnetic field, they are varying also in time, not only with space, also with time. So when you claim this, so you are saying that E and H both are varying sinusoidally. That's the meaning of inclusion of time harmonic stuff. For example, you're introducing something like e power j omega t to the equation. Yeah. See, in signals and systems, you might have learned Fourier transformation. Then what did you learn here? In Fourier transformation, you might have learned something, and that is, and this is a different really, okay? So whatever you have learned here, I think I might have told you already. So I think I just told you about this. So you know what happened once, I think whoever missed that, there was a conference. Yeah, there was a conference, and the conference was chaired by Mr. Lagrange and his best friend Euler, and also Laplace is chairing along with Lagrange and Euler. So Fourier, at the age of 17, okay, or less than that, he approached these guys with his paper. And in this paper, he mentioned about Fourier series and Fourier transformation. So he just took x of t, Mr. Fourier, Jean-Baptiste Joseph Fourier, he took a real function x of t and e power minus j omega t minus infinite to plus infinite. And this is complex spectrum x of j omega. This is t, it's dt. Now, we often by heart this way, right? X omega is equal to negative to positive integration x of t power minus j omega t. But Lagrange straight away rejected this article. He said that x of t is real quantity. You are multiplying this real quantity by a complex stuff e power negative j omega t. So deliberately you're making real stuff into complex stuff, and now you're going to say that you're enjoying a complex spectrum. So this is impossible. I can't accept this. Fourier has no answer at that time. Yeah. And again, he said that you can't represent a signal with coordinates. Okay, you can't. That means I can't express a signal with coordinates in Fourier series form. For example, a square wave, the abrupt discontinuity from high to low or low to high, whatever that is. If you have signals like that, I can't represent that using Fourier series. So he kept quiet. He can't do anything. But at that time, Simon de Laplace, he was in great favor of Fourier. He was supporting Fourier, but Lagrange and Euler, they are great guys. So just they rejected. Okay. So finally, everyone understood like this: this e power negative j omega is a kernel. This is a kernel. This guy, what it does, x of t has many frequency components in it. The hidden talent of x of t has many frequency components. So this e power negative j omega t is extracting various frequency components in x of t. And those frequency components just we collected, and now we are showing it as spectrum of frequency components. Yes or not? And way back, Sir Isaac Newton, he did this experiment. He took a prism like this. And when we incident say, I think you might have done your ICSE board, maybe in a CBW class, whatever. So if we incident white light on this prism, then what happens? Yeah, then you could see spectrum of colors in the other end of this. Okay, that is what we observe. That means this guy, this prism is something acting like kernel e power negative j omega t. This white light is something like x of t, and now you're seeing spectrum of colors. This is what like x of omega. Yeah, by general we just take everything as complex frequencies. Okay, so you have complex spectrum. So now again, how do we get this white light? Sir Isaac Newton, he just made this prism upside down, and now we are giving input to this upside down prism is band of colors. Now he observes something strange. We see the dispersions and all those effects we are not seeing here now. So now you have something like again white light. Now this upside down prism is acting like ultra kernel, let's say this is e power positive j omega t. Yeah. See, of course, I will not discuss all those things because how to find x of t? This x of t is equal to 1 by 2 pi integration of x omega e power j omega d omega. This 1 by 2 pi, can I take anything else other than 1 by 2 pi? This is just a scaling factor. I can take 1 by 4 pi, I can take 1 by 8 pi, or I can take square root of 8. Whatever you want, you can take. But if you take whatever you want, differentiation property, this property, will really hamper like anything. Not only this property, there are other properties. They will disturb. So otherwise, this guy 1 by 2 pi will not do anything with convergence. I can take anything. I can also take 1 by square root of 2 pi. If you're really interested, just go home and take some other scaling factor and just try to find its inverse. And in MATLAB, you try to go for spectrum and time domain function. You just check whether or not any problem with your time domain function. Absolutely, you see there's no problem, but what 1 by 2 pi does there. Okay, that's only to maintain some convenience in mathematical sense. Otherwise, that 1 by 2 pi has no big role in that. I can take anything. Yeah, so mathematicians really argue with this. Mathematicians says, why only 1 by 2 pi? But engineers says that I must always take 1 by 2 pi. Okay, so there is again a big debate in these things. Like Coulomb's took k is equal to 1 by 4 pi epsilon naught. There was a very big reason. Just many argued, but there was a big reason. But finally, he won the race. Okay, so we will take a quick 5 minutes break, and after this break, we will solve problems on polarization. Okay, you can take 5 minutes break now. Shall we start? Shall we start? You can speak out. I just unplugged my mic. Are you there? Shall we start? Can
Yes,
you
sir.
hear?
Yes, sir. Yes, sir.
Okay. Again, I'm using my mic. So let us solve some previous gate problems. So I'm using my mic. I cannot hear you. If you have anything, just text me on chat box. Okay, thank you. So let's solve some gate problems. So fortunately, you have really simple problems from polarization. Other problems may hamper us, but you will enjoy this. Okay, maybe this bolsters your your view towards gate, or this may beef up your views towards gate. For example, it's given like this: electric field. One of the papers given this one, electric field is given to you as 0.5 ax roof plus it's given ay roof, okay, and multiplied j omega t minus beta z. All right, so he's asking what kind of polarization this exhibits. This E is exhibiting on the transverse plane. So the options are given to you like this: linear polarization, and this is right hand elliptical polarization, and left hand elliptical polarization, and none. So I'm just unplugging my mic. Just please tell me what could be the answer. You can speak out. Yes,
Linear.
yeah, linear. Great. That's it. Yeah, you can crack gate now. Gate is this symbol. How did you say it is linear polarization?
Sir, e power 0, sir. The phase angle is 0.
Yeah,
Phase difference.
okay. You could say there is okay. The thing is that there is no phase difference. First of all, for example, you see you're right. Means of course you're right. Omega t minus beta z. Say it is some theta. Okay, say it is e power z theta. That means this guy is common between these two components. Okay, I have EA component here, and I have say EX component we have here, and we have say EY component. There is no phase difference between these two guys. So therefore we could say this is perfectly linear polarization. So in this case, you have Ex equal to half, and this coefficient is 1. That means Ey is equal to 1, but this doesn't hamper linear polarization. Whether amplitudes are same or unequal doesn't matter, as long as we have same phase, or as long as there is no phase difference, then definitely we can say something is near. But this is only for 1 mark, okay? And negative marking is what, if you go for incorrect option, you will definitely say you will have to enjoy this. You have to deprive this 1/3 mark. And for God's sake, at least one can say that there is no elliptical polarization. Okay, so because amplitudes are different, so people will definitely go for RSGP, LSGP. Okay, if you're really confused in this, you may either choose RSGP or LSGP, thinking that this is some phase between Ex and Ey. So please don't think like that. So if you took this phase out, otherwise this is like this. So you have 0.5 e power j omega t minus beta z ax roof, plus again you have 1 multiplied by e power j omega t minus beta z, and this is along y-axis. All right. So yeah, you can compare with the original one. That is what you have, like EA along a roof, plus you have here EB multiplied by e power j delta. Okay, this is like you have here e power j theta. This is common phase, and you have the oscillations e power negative j k dot r. If it is e power negative j, it's going in the forward direction. So now you have e power j theta, but do you have delta here? Do you have delta here? No? Yes or no? Yeah.
No, sir,
No,
0, sir.
sir.
Yeah.
No,
So
sir.
delta
No,
is
sir.
0. So therefore, we could say it is. So this is more general, okay? And of course, also you have point K sphere. You have something like point K sphere. That also we will see. And you have, this is what your hemisphere, say north hemisphere, south hemisphere, for example, and this is what your equatorial margin like this. So along the equators, always you see linear polarization. Okay, here you see always circular polarization. Other than these two, always you see elliptical polarization. So this is very much useful in antennas terminology. And if we have time, we will see about this point. That means we need to map whatever polarization study we are going to do now. We can map it on this point sphere. Okay, so if we have time, we will go through this. Otherwise, we will say bye bye to this. Again, I'm using mic. If you have anything, you can just uh, you can text me on again chat box. So it is simple. Let me go for this again. You have one more. Okay, if I ask you what is direction of E in the previous question, if I ask you what is the direction of E, because you have two components, right? I have some say 0.5 e power j omega t minus beta z ax roof, plus I have 1 e power j omega t minus beta z ay roof. So I have ex component and ey component. That means you have something like, say, this is your x-axis, this is your y, this is also z-axis. So I have something along x-axis now. Okay, say some 0.5 along x-axis, and I have something along y. This is bigger one. This is one compared to this. So this is occupying this. Okay, say it is oscillating like this. It is oscillating this way along x-axis, along x and y axis. If I add these two now, what do we get? What could be my direction now? Because anyways, I must get, say, in this direction. So direction of E is equal to what?
Tan
Tan
inverse of y
inverse.
by y by x.
Tan inverse, say I can take 1 over 0.5. This is what my direction, okay? And what could be my magnitude? My magnitude could be square root of 0. Square root of 0.5 square plus this guy 1 square. This is what my magnitude. So direction of E is this, okay? And also I can find its magnitude like this one. All right, next one is this. Now here is another interesting previous gate question. Say E is equal to AX plus J AY. This is E power negative J beta Z. You just tell me one simple point. I'm just unplugging my mic. You just tell me wave is propagating along positive G axis, true or false? I unplugged my mic. You can speak out. Wave is
True.
propagating along positive G axis, true or false?
True, sir.
Yes?
True, sir. True.
Yeah,
Sir,
fine.
is answer true?
Because I have in the exponent, I have negative.
Negative value, sir.
Yeah,
Yes.
so that is it's nothing but e power negative j beta of positive z. This indicates this guy is traveling along positive g axis. Now you tell me, you have options like this. You have right hand elliptical polarization, right hand circular polarization, left hand circular polarization, and linear polarization. Which among these four is going to fit this option? This question. What do you think? How many of you vote for linear polarization? You can speak out. Okay, one of you said one of your friends said, I mean, left-handed circular polarization. How many of you accept this? How many of you accept this? No one, but your friend is correct. I just want to know who just said. Kishore Yadav, very good. Kishore Yadav is left-handed circular polarization. Why? Because there is a phase
Sir,
shift
J
of
can be represented as
90
e
degrees.
power by
No, how I can do this? So this one, E, I just go for its solution. So E is equal to, what do I have? I have AX roof, E power J beta Z, plus I have AY roof. And this J, we can write it down like this, E power positive J pi by 2. Okay, E power positive J pi by 2. And again, you have to multiply this with E power negative J beta Z. All right, you can compare with the usual technique. You have EA, that means you have like this EA, and this is say like a roof, and you have like EB and E power Z delta. Okay, so E power Z delta B, and you have any common phase, anything, E power Z theta, and this is what direction of wave travel. Okay, E power negative J K dot R. All right, so now what is delta here? In this case, what is delta meant? So I have
pi
E
by
is
2.
equal to 1 and also EB equal to 1 and delta equal to positive 90. Okay, so delta equal to positive 90. So therefore you must take, this is left-handed circular polarization, because if I take the magnitudes, so generally EA and of course EB, they're complex. So I take the same magnitudes, EA is equal to EB because EA is equal to 1, EB also equal to 1. It is rotating, yeah, clockwise on transverse plane, tracing circle otherwise on transverse plane. So if you want to check it in conventional way, you go this way like this. So for example, you see I just take a transverse plane. Let me take, okay, I have a transverse plane. Take it this way. Okay, so okay. This is my X, say this is my Y. Okay, so X cross Y is G. Now what do? Just go and you plug in the values for G. Okay, I can take, there is phase difference here 90 degree between these two. You can take this transverse plane, you plot on this, and you must get same stuff, otherwise you will understand this. Y leads, the component of Y leads X by 90 degrees. As a component of Y leads X by 90 degrees, you can say you have left-handed circular polarization. Okay. Otherwise, you can just draw in the form of vectors. You would see a trace like this. You would see a trace. So, trace you will see like this. Okay, we are taking omega t equal to 0, omega t equal to say pi by 2. Now you take pi by 4, or you can take pi by 8, pi by 4, so on. You can take pi by 2, so on. You can take, you will see all these things. In this case, you don't have any omega t. If you want, you can also take omega t. So beta z, see, if you want to draw something on this transverse plane, just put z equal to 0. If you put z equal to 0, now we are sitting on this transverse plane somewhere here. Z equal to 0 means this. Okay, now we just start playing with this. Now you just start playing with this, you'll get the answer. That's it. So I'll go for one more. Okay, this one we can knuckle down this one very easily. So electric field is given to you as 5 cos omega t minus beta z ax roof, plus one more is given to you 10 sine omega t minus all our previous year papers beta z ay. Let me give you options: linear polarization, circular polarization, elliptical polarization, and okay, this is C. And let me take D, unpolarized. Oh, you have some peculiar option, unpolarized. I'm unplugging my mic. Just give me the answer. Which one do you think fits this question? Hmm? Which one do you think fit this question? 5 cos omega t plus 10 sin omega t. First of all, you just confirm whether it is polarized or not. Is this polarized or not? I just unplugged my mic. You can speak out. Is this polarized or not? Will somebody speak out, please?
Sir, yes, sir.
Yeah. How do you confirm that?
Sir, because we have AX and AY. Sir.
Very good. Anyways, you're right. So that's smart. So yeah. So I have EX component here and also EY component. And I can see oscillations. I mean, I can see polarization along x-axis, EX is along x, and EY is along y. All right, so EX is oscillating along x-axis and EY is oscillating along y-axis. So if I combine these two effects, I may get some other effect. Okay, so first of all, this is incorrect. So it is polarized. Now you have to select one among these three. Now, which
Sir,
one do you think?
elliptical, sir.
Yeah,
Yes, sir.
Elliptical, sir.
elliptical.
Yes, sir.
Very good. But how?
Magnitudes are different, sir.
Not equal, no, sir.
Yeah,
Magnitudes. And they have
magnitude
a
is
phase difference
different,
of
and
90
there is an 90-degree phase shift between sine and
cos.
cos.
Yes, sir.
Yes or not? So
Yes,
just
sir.
go home and you do these things, you will get the answer. Okay. So could you tell me which elliptical polarization is it, RHEP or LHEP? Which one do you think is going to win the race? RHEP or LHEP? Yeah.
LHE.
Yes.
Sir,
LHE.
LH.
Sure. Are you sure? Think of it again. Which one do you think is correct? You freeze it first of all, otherwise do one thing, you take omega t equal to 0. Okay, you take omega t equal to 0. And also, of course, if I take z equal to 0, I will be sitting on this transverse plane. I also take z equal to 0. Okay, so omega t equal to 0 first. Of course, z equal to 0 already. So z equal to 0, first of all, fix it. You fix it. Someone answered me, LHCP. Okay, but okay, wait a minute. We will confirm this. So fix this guy, and now you vary this omega t. You vary omega t all the way from 0. It takes some interval, say some pi by 2, pi, so on like this. Now, first case is this, omega t equal to 0, z equal to 0. So now what you get 5. So 5 AX. So you have something like this. Okay, 5 AX along x-axis. Now, what about this? Omega t equal to 0, z equal to 0, sine 0 is 0. So there is no y component for, you have only x component for this case. Now, case 2 is this, omega t equal to pi by 2, and of course z equal to 0. If I take omega t is equal to pi by 2, and of course z equal to 0, omega t equal to pi by 2, now this guy will be ruled out. So cos 90 is 0, this guy is ruled out. So sine 90 is positive 1. Now you tell me, positive 1. So now where do we go? Now where do we go here?
Along Y, sir, possible.
Like this, right?
Yes, sir. Yes, sir.
We are going this way. And this is, say, if I take this This is magnitude 5 and this is 10. Agree? Agree?
Yes, sir.
Yeah. Now again, case 3, just go for omega t equal to pi. Now if you put omega t equal to pi here, omega t equal to pi, beta, I mean z equal to 0, omega t equal to pi. What is sine pi? Sine pi is gone, 0. What is cos pi? Cos pi is
-1, sir.
1, so therefore you get negative 5. Now how are you moving here?
Along -x, 5, sir.
Yeah, of course, this is along x, I mean negative x-axis. All right. Cos pi is what? Negative 1, right? So 5 multiplied by negative x roof. So you come this way. That means we started here and now we are moving like this, right? Now we just follow IEEE convention. You take your right hand rule, all right hand rule, you take it, and this is along say positive z axis, and this curl is what? This is your right hand, right? This is your right hand. So 10 is not equal to 5. So therefore you have right hand elliptical polarization. But physics community argue this and they say it is left hand elliptical polarization. But we follow one standard. Institute of Electrical and Electronic Engineers Society or community is this. Okay. So anyways, so this is simple. Let's solve one last problem. There is one last problem, and of course, do you have any questions here? Until now, do you have any questions? Okay. So pin drop silence means either no questions or nothing you understood. Okay. I'm just using mic again. You cannot speak out. So let me take this is gate 2015. So gate 2015 set 2. Okay, so it's given like this: the electric field of a uniform plane wave, the electric field of a uniform plane wave, otherwise I can take of uniform plane EM wave. Okay, anyways, I can take also plane EM wave or whatever you want, you can take. Uniform plane electromagnetic wave is given like this: E is equal to AX roof plus J4 AY. All right, and it's given to you like this: E power J 2 pi 10 power 7t minus 0.2 z. Okay, see, the question is straightforward. You know, the polarization of the wave is, it's a one mark question. The polarization of the wave is, okay, let me give you options: right hand circular polarization and right hand elliptical polarization. So left hand circular polarization, and last one is left hand elliptical polarization. Which one do you think? I just unplugged my mic, you can speak out. Yeah, so which one do you think is correct?
Left hand circular polarization, sir.
Circular how? Just
No,
Sir,
sir.
left hand
Left hand elliptical
polarization.
polarization. Elliptical,
very
sir.
good. That's it here. Yeah, I think you just compare with the original one, right? So I have here e power j pi by 2 delta equal to positive pi by 2. So therefore it is left hand elliptical polarization. That's it. Do we have any common phase in this question? Do you have any common phase? No, there is no common phase mentioned in this question. So you have time harmonic stuff, you have e power j omega t, and wave is propagating along positive g axis while polarized on the xy plane. Yeah. So this is simple. This is simply left hand elliptical polarization. You just otherwise, if you want to really, if you want to go in conventional way, I can take direct form. That depends whatever we have in terms of delta, theta, all these things. Otherwise, you can construct this equation or rearrange that equation like this. Just take real part of this. Okay, you just take real part of this stuff. If I take real part of this stuff, let me put it down here. Okay, let me cut this. Let me use black. Okay. So now from this, I can write down E is equal to cos omega t minus beta z ax roof plus 4 cos omega t minus beta z plus pi by 2 ay. I have j, I can write j is equal to e power j pi by 2. I'm just taking its real stuff. So therefore it is, I'm just showing this in the argument, that is positive pi by 2. This is positive pi by 2. And you have coefficient here 1, you have coefficient here 4. Okay. And now you can plug in omega is equal to this 2 pi 10 power 7. Okay. And beta equal to, you have 0.2. You can plug for this beta. You can do whatever. So this is what your stuff. And further, so E is equal to cos omega t minus beta c. For gate, in gate examination, please don't do all these things. Take your general form, compare and get the answer. That's it. So what is cos 90 plus something? That is negative sign. So therefore I get minus 4 sine omega t minus beta z along ay. So let me cut this. So I just copied. Okay, so E is equal to this. So now wave is traveling along positive z. So wave is traveling, propagating along positive z axis. Okay, so yeah, so let me take down like this. This is like, say, let me take this is x, this is Mr. Y. So I take at z equal to 0. When I say z equal to 0, see wave is propagating towards u. So I take z equal to 0. So my z equal to 0 means this point. Now I'm resting on the transverse plane. I want to play on my transverse plane now. Okay. So I just take z equal to 0. So z equal to 0. So z equal to 0. Now just start with this. Now what is your case 1? Omega t equal to 0. If I take omega t equal to 0, okay. Now this is cos 0, it is 1, sin 0, it is 0. So therefore I'm resting on this. All right. I'm resting on this along x-axis now. That's it. Now, red is looking dangerous. So anyways, case 2. Case 2 is omega 2 is equal, let me take pi by 2. If I take pi by 2, so cos pi by 2. So cos pi by 2 is 0. So sine pi by 2 is positive 1. So this is, now it is negative 4, right? So negative 4 means I must come all the way down like this. So I must come down. Okay, so that's it. Yeah, it's a bigger one. because its amplitude is 1, this is 4. All right, so I just came all the way like this. You take omega t is equal to now pi. So cos pi, if I take this as pi, cos pi is -1, sin pi, this goes to 0. So you have -1. So therefore, you must come like this. All right. And similarly, if I take 3 pi by 2, pi plus pi by 2, 3 pi by 2, so cos 90 is 0. So you have sine 90, I mean sine, this is 270. So sine 270 is what? -1. So negative into negative, positive 4, okay? So therefore you must go up now. Here you must go up. All right. So don't forget this. First of all, the moment you go from here to here, first arrange like this. That means your journey is this now. Okay, just trace it, man. If I trace it, you have an ellipse. My ellipse is like something else. But if I add these two, okay, if I add these two, you get resultant vector somewhere between these two, and directions you can find just like that. Okay, you have unequal amplitude. So therefore, you just take your left hand. You just take your left hand, elliptical polarization. Okay, so this is your, my thumb is, okay, I think it is like this. It's propagating along Z. Yeah, and now this is your left hand. It is curling like this. Therefore, it is left hand elliptical polarization. All right. So, so what do you comment on gate questions? I just unplugged my mic again. You can speak out. Is gate questions are simple here? Is gate questions are simple?
Yes,
Yeah.
sir.
Yeah, it's very simple, but soon or later we will see other questions. You will really feel that gate questions every time they are not simple. Sometimes they really disturb us. But anyways, so we will what we do. So we will solve one simple question. This is again a previous year question. So 1 second, please. Not 1 second, 10 seconds. Okay, so I just think again previous year question. An EM wave, an electromagnetic wave traveling in a conductor medium. So conductor means my electromagnetic wave, they hate traveling through conducting medium because sigma is very high. So it just is prone to high losses. So just really don't encourage this, but still the problem is given to you. Let's accept. An EM wave traveling in a conductor medium and has attained a wavelength of lambda and has attained a wavelength of lambda at a frequency say f1. Now when frequency is doubled, say when frequency is doubled, what is the corresponding wavelength? What is, yeah, this total question again asked in gate examination. What is the corresponding wavelength? Anyone? Anyone? Okay. This is section A. Okay, sorry, I just proved this for section C. Already it is over. I should not have asked this question of you. But anyways, let me solve it down here. Anyway, so see, I know, do we know this? Gamma is equal to, I know, what I know, J omega mu. Okay, I must have. And this is what here, sigma plus j omega epsilon. So gamma is equal to, we have this. Okay. Now this is a conductor medium. So in conductor medium, sorry. So in conductor, if I take conductor medium, loss tangent is far greater than 1. That means sigma is far greater than, say, omega epsilon. So if I use this stuff here, I just want to take sigma common. If I take the sigma common, so j omega mu, and from this, I just take sigma common. So let me take sigma common. So you have 1 plus j omega epsilon by sigma. All right. So let me put it down. So this guy is sitting inside a square root. Okay. Now, if sigma is far greater than omega epsilon, so omega epsilon by sigma is far less than 1. So this fellow is now far less than 1. So when I compare with this one, this guy is far less than 1. So I can neglect this guy. So therefore, gamma is approximately equal to now j omega mu sigma under square root. Okay, this is nothing but omega mu sigma. Yeah, so I can take, this is 45 degrees. I think I just proved it. What is square root of j? So I can write this guy, I can write this j as e power j pi by 2. Because this is cos pi by 2 plus j sin pi by 2. Cos pi by 2 is 0, so sin pi by 2 is 1. Write it down. So this is nothing but cos pi by 2 plus j sin pi by 2. So cos pi by 2 is 0, sin pi by 2 is 1. So it is j. So I can write it down as e power j pi by 2, and this is square root again. Okay. So the square root, whatever I have, e power j pi by 2, and square root, we can write it down as 1 by 2. So with this, what I can do now is, what I can do is this. So e power j pi by 2, I have 1 by 2 in exponent. So I multiply this, I get e power j pi by 4. E power j pi by 4 is cos pi by 4 plus j sin pi by 4. So just use it here. So we get now what? Cos pi by 4 is 1 over root 2, also sin pi by 4. So therefore, gamma is equal to, we have alpha plus j beta. So alpha plus j beta is equal to, now you get omega mu sigma by 2 plus you get j omega mu sigma by 2. Okay. Now what is the question here? An EM wave traveling in a conductor medium and has a time, because see, as of now we are discussing, I mean, we just discussed with high loss medium, because conductor medium is high loss medium. So in high loss medium, loss tangent is far greater than 1. So therefore we came to this conclusion now, and has attained a wavelength of lambda at a frequency of 1. Okay. When frequency is doubled, what is the corresponding wavelength? Now I'm just unplugging my mic. You can speak out if you know the answer. Anyone? Anyone, please. This is the previous gate question. I proved it also here. Just no, you can tell me now. So alpha is equal to this stuff.
Sir, by root 2, sir. Lambda by root 2.
Okay. Now, okay, just tell me which one do I need to take now? Whether I can take alpha or beta in this problem. For this problem, whom do we require? Alpha or beta? Whom do we require for this problem? Alpha or beta?
Sir, beta, sir.
Very good. So we require beta for this. Why? Because I know beta is equal to 2 pi by lambda. So I can get something here. You see, because take in a conductor medium. In a conductor medium, so I can say, I can take whatever we proved a moment ago, omega mu sigma by 2 under square root. Now I know very well Mr. B is equal to 2 pi over lambda, phase constant 2 pi over lambda is equal to omega mu sigma over 2. That's it. Okay. Now further, I can plug in this. This guy is nothing but 2 pi f. If I plug in here, now what you get here, 2 will cancel out internally. So now you have pi f mu sigma. Agree? So
Yes, sir.
once you have this, can I say like this now from this? I can say that. So 1 by lambda is proportional to square root of f. Can I say this?
Yes, sir.
For lambda, I have square root of f here. So therefore, see, this a traveling wave in conducting medium has a kind of wavelength of lambda at, okay, this is the lambda 1. I can take this is lambda 1. Lambda 1 at a frequency of 1. Okay. Now when frequency is doubled, what is the corresponding wavelength? Yeah. Can I say like this? Lambda 2, let me write this. Lambda 2 equal to lambda 1 over square root of 2. Can I say this?
Yes, sir. Yes, sir.
Obviously 0.707 lambda 1. So lambda 2 is less now. So obviously wavelength is decreasing now. Okay, so that's it. It's very simple. Just confirm with this. You'll get that. Okay. So for 1 by lambda 1, you have square root of f1. So 1 by lambda 2 is what? So frequency is doubled here. So for 1 by lambda 2, you'll be having square root of 2f, I mean this 2f1. So that means lambda 2 is equal to lambda 1 by root 2, or lambda 2 is equal to this. And that's it for today. So these kind of questions are quite common in GATE examination. But anyways, there is no big, that means we must be able to identify the right term. Okay. So the moment he gave us your conducting stuff, this is conducting medium or conductor medium, and he's talking about wavelength and frequency, then straightforward I must go to beta. You must be very quick in this. Just go to beta set, because beta, in this beta I have lambda associated with, but not with alpha. I'll see for conducting medium, alpha is also equal to same formula, I mean same formula, whatever, but alpha you can't express in terms of lambda. So therefore you have a flexibility of expression in terms of lambda, 2 pi by lambda. You can now work out with this. So that's it for today. Do you have any questions here? Do you have any questions, please? Yes or no? Yes or no? Yes?
No, sir.
Yeah, okay, fine. Thank you.